Section 4.2, 4.3, Patterns with linear and nonlinear functions. The independent variable is the variable that is the input of a function. The dependent variable is the variable that is the output of the function. The value of the dependent variable depends on, or is a function of, the value of the independent variable. What is the relationship between the number of rectangles and the perimeter of the figure they form? Represent the relationship using a table, equation, and graph. So filling in the table is fairly easy for the top line. Number of rectangles, we just count. So we've got 1, 2, 3, and 4. Then determining perimeter, we have to remember perimeter is the sum of the length of the sides. So for one rectangle, we've got 6 plus 6 plus 1 plus 1, which gives us a perimeter of 14. For 2, it's 6 plus 1 plus 1 plus 6 plus 1 plus 1, which gives us 16. And then for 3, we get 18. And for 4, we get a perimeter of 20. To represent this as an equation, we have to think about what's happening between the increase in the number of rectangles. So when we go from 1 to 2, our perimeter changes by 2. It adds 2. And then we go from 2 to 3 rectangles. We add 2 to the perimeter as well. And then from 3 to 4, we add 2 as well. So in order to create an equation for this, I want you to think about what we need to plug in where. Well, we know in an equation we've got our dependent variable, y, is going to equal some combination of a number and x, and then there's probably going to be a constant in here. So luckily for us, we've already figured out our pattern. It's plus 2, and that 2 is the value that goes with the x. So we're going to put 2x here. Now to figure out what the constant is that needs to be added to this, all we really need to do is think about what happens when you plug 1 in for x. You get 2 times 1 is 2. In order to make that 14, we would have to add 12 to this. So this becomes your equation, y equals 2x plus 12. If we want to test it, we can try plugging 2 in for x and see if we get 16. So 2 times 2 is 4, plus 12 is 16. So it fits the pattern. And the last thing we need to do is represent this graphically. So we're going to graph it. Let's go 1, 2, 3, 4. And then let's say this counts by 2. So we'll go 2, 4, 6, 8, 10, 12, 14, 16, 18, and 20. So at 1, we got a dot at 14. At 2, we've got one at 16, 3 at 18, and 4 at 20, or 20 at 4. And that is our representation graphically. All right, so the next part is we have the definition for a function. A function is a relationship that pairs one independent variable, or input, with exactly one dependent variable, or output. A linear function is a function that has a graph that makes a straight line. So it's a function that when graphed makes a straight line. Linear functions always have a constant change by adding or subtracting only. So when you go to find the pattern with a linear function, you're going to notice that the pattern is going from 1 to 2 was like what we just saw. They're adding to, adding to, adding to. To write equations for linear functions, and this is important, so star this, you're going to need this, and we kind of already used it. We want to find the constant change in the y values and multiply that by x. So the constant change is going to be addition or subtraction, but we're taking the number that's getting added or subtracted by in the change for the y's, and we're going to put that next to the x through multiplication. And then we add or subtract by a constant to help fit the pattern. And that's what we just did in the first example. And the more we practice, the more it'll make sense. So in this problem, we want to first determine whether or not this is a function. And we do that by checking to see if every input goes to one output. We also want to check and make sure it's a linear function. So we need to determine whether or not it's increasing by a constant value. So 0, 1, 2, 3, 4, 1, 2, 3 all go to unique outputs, so we're good there. It's definitely a function, but is it a linear function? Well, from 8 to 10, they're adding 2. From 10 to 12, they're adding 2. And from 2 to 14, or 12 to 14, they're adding 2. So we have a constant increase of plus 2. So yes, the increase, it increases by a constant. So it's definitely a function, and it's definitely a linear function. The next part of this, they want us to write the equation. And in order to do that, we start by writing our dependent variable. And then we think about what was the constant increase? Well, it was plus 2. So that constant increase of 2 is what gets placed next to your x. So it becomes 2x. And then we have to think about, well, if we were to plug 0 in here for x, we'd get 2 times 0 would be 0. But we need to get to 8, so that means our constant that we need to add has to be 8. So our equation becomes y equals 2x plus 8. Next problem. We are given a table of talking about the number of triangles to perimeter, and they ask us, is this a function? Well, I can tell you it is, so I want to focus more solely on whether or not it's a linear function. So let's talk about whether or not it's a linear function. So we got to look at our output, in this case perimeter, to see if there's a pattern. Well, from 10 to 14, they're adding 4. From 14 to 18, they're adding 4. And from 18 to 22, they're adding 4. So this is definitely a linear function. It's increasing by a constant. And that constant is 4. All right, so now we need to figure out what our equation will be. Well, we talked about this in the last problem. You start with your dependent variable equals, and in this case we have our pattern. In this case we're increasing by a constant of 4, so we put 4 here, so it becomes 4x. And then we think about what has to be added or subtracted from this to give us our output for one of these values. So if we plugged 1 in here, we'd get 4 times 1 is 4, and then to get to 10 we'd have to add 6 to that. So y equals 4x plus 6 is our equation. Next example. Once again, let's worry about whether or not this is a linear function, not just a function. All right, because I'm pretty certain it's a function. 1, 2, 3, and they're all going to outputs. That's a function. So let's talk about whether or not it's linear or not. So from 8 to 1, subtracting 7. From 1 to negative 6, subtracting 7. From negative 6 to negative 13, subtracting 7. So this is definitely a linear function. It's got a constant pattern, and it's decreasing by 7 constantly. So now we have to write our equation. Well, once again, we start with our dependent variable equals our constant of change with our x, and then we determine, well, all right, if we plug 0 in here, 0 times negative 7 is 0, and in order for that to get to 8, we need to put a plus 8 here. So our equation becomes y equals negative 7 plus 8. Now we're going to talk about nonlinear functions. A nonlinear function is a function whose graph is not a line or not part of a line. So these are some of the examples of linear functions, and these are some of the examples of nonlinear functions. We've got parabolas, hyperbolas, and then the absolute value graph. So parabolas, you might remember this, parabolas, x squared being the general form, and the absolute value, we just learned this, y equals absolute value of x. All right, but we'll talk about all these as we go through the unit. All right, so here, they've given us a table of values, and they want us to graph and determine whether or not it's linear or nonlinear function. We can also do this by just looking at the pattern of the graph itself. So if we look at the graphs, the y values, and think about how each one changes. Well, here we subtract 3, then we subtract 1, then we subtract 1. Because this pattern is not the same throughout, I'm fairly certain this is going to be a nonlinear function. but let's just graph it to be safe. So here I've graphed the ordered pairs of points. So at x is 1, y is 6, I put a point. At 2, 3, I put a point. At 3, 2, and at 6, 1, I put a point. And if we look carefully at this, we should notice that this particular graph isn't a straight line. It appears to curve. So that means this is definitely nonlinear. All right, in the next example, we can kind of take the same approach. They've given us values. We can look at the table first to determine, or we can graph it, or we can do both. So if we look at the table here, to go from -4 to 2, they had to add 6. From 2 to 8, they added 6. And then from 8 to 14, they added 6. So this is a constant addition of 6. So I'm fairly certain this is going to be linear. So let's go ahead and take a second and graph these points at 0, -4, 1, 2, 2, 8, and 3, 14, and see if it is or not. It might be helpful to make sure that you try counting by 2 on your graph in order to fit these large values in there. So instead of having every line represent 1, have it represent 2. So after graphing these points, it's fairly obvious that this is a linear function. So if we were to draw a line, it would connect in a nice straight pattern here. And so this one has to be a linear function. Our change is constant. All right, so now in this example, they want us to tell from just looking at the graph whether or not it's linear or nonlinear. And remember, linear means it looks like it's a straight line. Nonlinear, clearly not a straight line. So in the first example, it's got a curve. It's kind of like a wave. So this is definitely nonlinear. This is a straight line increasing to the right, so this is linear. And then the last one, this is a parabola, and because it's a parabola, I know it curves, so this is nonlinear. If the change in y values is by a constant or is by constantly multiplying, use that number as the base to the x power. If there is no real pattern in the change in the y values, try raising x to different powers, like x to the 5th power. These are just some helpful hints as we go to the next section where we talk about writing function rules. So for the first one, these ordered pairs represent a function, and we want to try to write a rule that represents the function. So the first thing we need to do is identify the pattern that changes in the dependent variables. So look at the change from y to y. So this would be +2. Uh-oh, but this isn't +4. Okay, so let's go back to the beginning and say, instead of +2, what else could be taking place here? Well, 2 to 4 could be ×2. Okay, and then from 4 to 8, that's ×2. And then 8 to 16, ×2. And then 16 to 32, ×2. Well, in the last slide, we talked about it, and it said if the change in the y values is constantly multiplying, we want to try using that number that it's multiplying by as the base raised to the x power. So in this case, we're constantly multiplying by 2. So that means our equation might be y equals 2 to the x power. Let's test it and see. If I plug in 1 for x, 2 to the 1st power is 2, so that works. If I plug in 2 for x, I get 2 squared, which is 4, that works. And then try 3, 2 to the 3rd power is 2 times 2 times 2, which is 8, so that works. So this is our equation. These get trickier, and when they get tricky, sometimes you've got to just try to use as many different equations you can to see if you can find one that fits, but most of the time we'll try to give these to you in multiple choice options so you kind of plug the values in and see which one works best. All right, the next one, same thing here. We want to test the pattern and see what we get. From 0 to 1, we're adding 1. Then 1 goes to 4, so they're adding 3. This doesn't look like a pattern. 4 to 9, they're adding 5. And then 9 to 16, they're adding 7. All right, so there's no real pattern here. But if you remember from that previous slide, it said if there is no real pattern, then you try raising your x to different powers. So that means we want to put y equals x, but we've got to put it raised to some power. Well, let's look at the numbers. 2 becomes 4 when you square it, so maybe x squared. So let's try this. If we plug in 0 for x, 0 squared is 0, so this one works. Plug in 1, 1 squared is 1, this one works. Plug in 2, 2 squared is 4, this one works. Plug in 3, 3 squared is 9, this one works. So this is our equation. And the next one, each set of ordered pairs represents a function. Write a rule that represents the function. So once again, we want to go ahead and figure out our y values. So 1 to 5 would be plus 4. 5 to 9 is plus 4. 9 to 13 plus 4. 13 to 17 plus 4. So this is something we're familiar with because we've got a constant increase by 4. And so this is just a linear function. So we'll start with y equals. Remember that your constant of increase is what goes with your x. So 4x. And then we've got to figure out at what piece we're adding to it is. So let's try plugging in 0 for x. 4 times 0 is 0, but we need it to equal 1, so we have to have a plus 1 here. Let's try plugging in 1 for x and see if we get 5 back. 4 times 1 is 4, plus 1 is 5, so that works for this one. 4 times 2 is 8, plus 1 is 9. So the pattern works for this equation, so we're good to go. All right, so on the last example, they want us to finish the pattern and then write the equation for the pattern. So in this case, they're increasing the number of figures and keeping track of the number of branches. So as we see here, from 3 to 9 is either adding 6 or multiplying by 3. Then they go from 9 to 27, so adding 6 is out. So let's say they're multiplying by 3. So then to go from 27 to the next one, we just multiply by 3, which means in this box we should get 81. And then if they continue the pattern, multiply by 3 one more time, this box should be 243. So our last 2 for 4 is 81, for 5 is 243, and the last thing we have to do is write our equation. Well, to write the equation, since we're multiplying by 3 each time, this is where we're going to use 3 as the base and raise it to the x power. So y equals 3 to the x power. And let's test this. 3 to the first power is 3, good. 3 to the second power is 9, that works. 3 to the third power is like 3 times 3 times 3, which is 27, so this equation works.